Welcome to the 40th lecture of graph theory. This is the last lecture. So, in the last class we looked at Hartwig's conjecture. To remind you what was Hartwig's conjecture. So the Hartwig's conjecture stated that if the chromatic number of the graph is greater than or equal to R, then the graph G has a KR minor in it. What is a KR minor? A minor on minor that is isomorphic to the complete graph on R vertices. So, for example, we saw that if the planar graph requires, for example, to understand this thing, if the planar graph, if suppose there is a planar graph which requires 5 colors to color, a planar graph which needs 5 colors to color, that means the chromatic number of G being greater than or equal to 5, then we will have a K5 minor in it. But then we know that the planar graph cannot have a K5 minor. Why? Because if you contract the edges of a planar graph, it will still be planar, and then these minor operations will always, any minor of a planar graph has to be still planar, but K5 is not planar. So, this Hartwig's conjecture, if true, will imply the 4 color theorem. So, that means every planar graph has to be colorable using 4 colors. So, of course, so this is a much stronger statement, much more general statement than the 4 color theorem. So, this says that it is not only for planar graphs, every time a graph can be colored, if a graph's chromatic number is at least R, then there exists a KR minor. In other words, if a graph does not have a KR plus 1 minor, we are sure that it can be vertex colored using at most R colors. This is what Hartwig's conjecture says. Now, the Hartwig's conjecture is not yet proved. It remains as one of the most challenging, difficult open problems in graph theory, but several special cases are already proved. Like for instance, when the chromatic number is equal to 5, that correspond to the 4 color theorem, and a little more than that. For instance, that is why the 4 color theorem follows from R equal to 5 case. So, R equal to 6 case is also proved by Robertson and Seymour, and then but later cases are still open, while then of course, there are several special classes of graphs for which Hartwig's conjecture is true. For examples, we can consider the perfect graphs where the Hartwig's conjecture is trivially true. Why is it trivially true? Because a perfect graph, if you remember the definition of the perfect graphs, they are the graphs whose chromatic number is equal to clique number, not only for the graph, also for all the induced subgraph. That is immaterial for us with respect to this problem, but we know that for perfect graph the chromatic number is equal to clique number. So, there exists a clique minor. If the chromatic number is equal to R, there exists a clique itself, not just a clique minor, there exists an induced clique there with R vertices. So, there is a clique minor also. So, the perfect graphs, it is trivial. So, now the question is other classes of graphs. So, for line graphs, it is known to be Hartwig conjecture is not to be true. For proper circular arc graphs, it is not to be true. So, there are several classes of graphs for which the Hartwig conjecture is not to be true. So, in this context, so we carry on from this point, and then we also want to mention some of these special cases which was proved by Kuhn and Osthus. So, suppose S is an integer, and then there exists an integer R as a corresponding function, as a function of S you can find another integer R s, such that the Hartwig conjecture holds for all graphs which does not contain KSS as a subgraph in it. KSS as a subgraph means that complete bipartite graph with one side S and another side S. If it is not part of the graph, then we can say that the Hartwig conjecture is true, not for every value of R, when R is sufficiently large, that is what it says. If for big enough values of R, the Hartwig conjecture will be true, is what this result of Kuhn and Osthus says. And now let us come to the topological minors. Up to Hartwig conjecture concerns with the existence of a complete graph as a minor. So, what about complete graph as a topological minor? So, is it true that if the chromatic number is greater than or equal to R, we have the complete graph as a topological minor itself? So, of course, to asking a complete graph as a topological minor is a much stricter, stronger requirement than asking for a complete graph as a minor. So, it is less possible, less probable, but this was also conjectured earlier. So, like Hartwig's conjecture, there was also a parallel conjecture called Hajo's conjecture. Hajo's conjecture, which stated exactly this: if the chromatic number of a graph is greater than or equal to R, then there exists a KR topological minor for the graph. But it turned out that the conjecture is wrong. After quite some number of, after several years, it was proved that there exists a counter example for Hajo's conjecture. It is not true in general, but after that it was even shown that not just one counter example, for almost all graphs the Hajo's conjecture is wrong. So, in a probabilistic sense, you can randomly select a graph and show that its chromatic number is something, but it will not have a KR minor of that corresponding chromatic number. And of course, several other methods to construct counter examples for Hajo's conjecture is known now. So, Hajo's conjecture turns out to be wrong, but still it was quite popular for several years. It was also very well studied. So, therefore, several results regarding in that direction is also there. So, for instance, there is you can compare this result of Kuhn and Osthus with their previous result. They say that if the girth is a little high, then the Hajo's conjecture is indeed true. Hajo's conjecture may be false, but only when the girth is small. So, they say that there exists a constant G such that all graphs G of girth at least G satisfy the implication. If the chromatic number is greater than or equal to R, then it has a KR topology, KR as a topological minor for all R. So, another way of asking, and another question, line of questioning is, so so what should be the average degree in terms of R, such that if I know that the graph has average degree at least this much, then we are sure that there exists a KR topological minor in the graph. So, it was shown by Mader that if the average degree is greater than or equal to some constant times R square, then we do have a KR as a topological, minor in the graph. We need the average degree to be quadratic in R square, C times R square. And of course, more or less this is the only possible thing. We can show that there exist some cases when it is below that you cannot expect a KR topological minor. In general, that is all we can tell about in terms the average degree requirement is that. But suppose we do not want a topological minor, we only want a minor, KR minor. Then what should be the average degree requirement? How much should be the average degree, so that we are sure that if the average degree is that much, then there is a KR minor for the graph. So, this question was answered by Kostochka. So, he showed that there exists a constant such that for every integer r, every graph G of average degree at least C times r root log r root log r times constant contains KR as a minor. We can compare it with the previous result, which says that if it is the average degree is at least C r square, then it contains KR as a topological minor. Here the requirement is much less, we do not need r square, we need only r root log r. So, and it is also known that up to the value of C, this constant can be improved a little bit probably than what Kostochka has done. It looks like it is also known which is the best constant. This bound is best possible as a function of r. You cannot hope to improve much. So, this is the best possible. Now, we are not giving the proofs of this result, neither the proof of the earlier result, because they are all more complicated, but we will to get taste of this kind of results, we will look at one result, the proof by proof of a, which is given by Diestel. So, to show that if the girth of the graph is high, then we can expect some dense minors in the graph. So, with that is about the of case. So, we will look at this result. This first it was proved by Thomason. He showed that, see, of case the earlier result says that if you have the average degree is at least CR root log r, then we do have a KR minor. But what if the average degree is not that much? Average degree, so suppose we just assured that the minimum degree is 3, whatever is r, we are assured that the minimum degree is 3, there is no more assurance on the average degree in terms of r, we are not told that the average degree is more than some function of r, but we know that every degree is at least 3. Then Thomason found out that if we simply increase the girth, if the girth is greater than or equal to some function fr, here girth is a function of r, then we do get a KR minor. This function is to be found out which is the correct function. So, but he has found out that there exists a function, so that if the girth is big enough, that is greater than or equal to that f of r, then even with the minimum degree 3 without any other restriction on average degree, we can expect to get, we can get a KR minor. This is interesting because when we fix the minimum degree at 3 and increase the girth without increasing the minimum degree say, then the graph will become sparse. Looking from one vertex, it will look like a tree like structure is going to some distance, right. It will become more and more sparse, but still we get as this girth requirement is increased, we do get bigger and bigger clique minors. We are sure that a KR minor exists if the girth is greater than or equal to f of r, right. So, now we will do a proof of this result, but for that we need a lemma developed by Diestel. So, that we can estimate this f of r also. So, this is the lemma. Let d comma k element of n, that means d and k are two integers with d greater than or equal to 3, and let g be a graph of minimum degree delta greater than or equal to d, and girth greater than or equal to 8k plus 3. Then G has a minor h of minimum degree delta of h greater than equal to d times d minus 1 raised to k. So, what this result says is, if your girth is high, so there is a value given here, girth is greater than equal to 8 k plus 3, and also the degree is high. Here we are not saying that the degree, minimum degree is only low at least 3, we are saying that minimum degree is at least d. Then we say that in terms of d and this k, k is in fact g minus the girth minus 3 by 8, right. We can get a lower bound for the minimum degree of the minor. That means we will get a dense minor, that is what it says, high minimum degree minor H is available, right. So, how do we prove this thing? So, to prove this thing, let us consider so a graph G with the given properties. That means its girth G is greater than equal to 8 k plus 3, this is what we have to remember. Its minimum degree is greater than equal to d, this is what we have to remember. And now we will collect vertices from G, let us say x. So, these are the set of vertices from G such that between any pair of vertices in G, the distance is, for instance, if u comma v element of x, then we need distance between u and v, shortest distance between u and v strictly greater than 2 k, this k being this k, right, strictly greater than 2 k. So, we can start with one vertex, if we can add one more, we add it, right. So, if we can add one more to this, we will add. So, to the extent that once you get to the situation that we cannot add any more vertex to this. So, one of the already existing vertex will have a problem if you add one more vertex to it, any vertex, any outside vertex is added to x. The distance between one of the already at least one of the already existing vertex will become less than equal to 2 k, that is why we cannot add. So, in such a situation, so we stop, we say that it is a maximal such set with this property, that pairwise distance between the vertices included in x is greater than 2 k. So, now what we are going to do is, so let us say these are the vertices of x, some vertices, though somehow I am just, so the thing is any distance here, the shortest distance here, it is not the geometric distance, it is the distance in the graph with the shortest distance in the graph, any pairwise distance will be greater than 2 k. Now, from each of these vertices we will develop a tree. First what we are doing is we will simultaneously develop a tree. So, for x, if this is the vertex x, then we will call t x, first we construct t x 0, then here this is y, we will construct t y 0, this is z, that is t z 0 and so on. And then after that in the next step we will construct t x 1 here by adding a few more vertices, then we will here we will construct t y 1 and here t z 1 and so on. So, what is this t x 0? T x 0 is this single vertex itself, right, each of them will be just single vertices, here this is x only, here this is y only, this is, and t x 1 is what? We will look at any vertex, we will collect the vertices which are at a distance of exactly 1 from this thing, so reachable at a distance of, say, from the not already taken vertices, we will take the vertices which are reachable in one step from any of these vertices. So, then we will add to one of them, for instance like this. So, in principle, for instance, if there is a vertex like this which can be added to this and this, we will add to only one of them, right, the arbitrarily choose to each. So, then we will get a few trees here, right, and then in the suppose in the ith step. So, in the next step what will we do? We will take all the vertices which are reachable in 2 hops at a distance of 2 from each of these vertices. in any of these vertices, and they will be attached to one of the trees which are already developed. It should be possible, because anyway if you track the shortest path to the set X, the just previous vertex is already attached to some of these trees, and then we can attach it to that, right, tree. So, like that we can construct Tx0, Tx1, like that we can keep constructing. So, Tx2, so up to Txi, and this will be done for each vertex in X. Say for each x element of X, we will construct this kind of trees, right. So, in the ith stage we will have several such, the one tree corresponding to each of those vertices in X, this many trees will be there, right. Now, to construct the I plus 1th tree, say Txi plus 1, this set of trees, what we do is we consider the vertices which are not already taken, in fact, which are at a distance of exactly I plus 1, which are reachable in I plus 1 hops from the set X, and then each of those vertices will be attached to exactly one tree in it. It is not that there is only one choice. It is possible that some vertices can be attached to more than one trees, but we will select one of them and then add to that, so that the trees remain disjoint. And it is clear that when we reach the 2kth step, the Tx2k and other things, for so then we have already covered all the vertices of the graph. That means every vertex of the graph belongs to one of these trees. So, that has become a partition of the tree. Now, some of these properties of these trees, for instance, I can call it Tx1. So, let us say this set is X equal to x1, x2, x something, x t or something. So, then we can say x1 to k, x Tx2 to k, these are the trees we have, Txt to k, where we have t is equal to the cardinality of x, right. These trees have certain properties. For one thing, each of them are induced trees in the graph. Why are the induced trees? So, let us see, suppose it is not. So, there is a tree here. So, this is one of those trees which we created. Suppose there is some edge here, but then I know that this vertex, the distance from here to here is at most 2k, and the distance from here to here is at most 2k. So, 2k plus 2k, 4k plus this edge together will make 4k plus 1 cycle, but we know that the girth of the graph is 8k plus 3 or more. So, this is definitely less than this. So, this is not possible, such a cycle will not exist. So, that is why this trees has to be induced. We cannot have an extra edge there. We cannot have an extra edge, because if we have an extra edge, we will get a cycle, and this cycle is definitely of length at most 4k plus 1. So, therefore, these are all induced trees. That means, any edge which is going out of this tree has to go to other trees, that connect it to other trees. So, our plan is to contract each of these induced trees, and get a minor. So, let us call it H. So, this will be the minor which will be created H, which the minor H which will be created from this graph. So, our intention is to show that this H minor is the kind of minor we want. That means, of minimum degree greater than or equal to d into d minus 1 raised to k. That is what we claimed in our proof, right, d into d minus 1 raised to k. This is what we want to show. To show that, first observation is all the edges going out of these trees, because this is an induced tree, should go to other trees, other branch sets. These are all branch sets now, right. But is it possible that one edge going out of here and one edge going out of both goes to the same tree? Because the problem is, if you contract this and this contract, that will become parallel edges, and then we will lose one edge unnecessarily. We do not want to lose any edge. So, we want to say that each of the edge which is going out of this tree will go to different trees. It will not go to the same tree, because if two different edges from this tree goes to the same other tree, then when we contract this tree and contract that tree, it will become parallel edge, and one of them we will lose. We want all the edges which are going out of this tree to become finally count as the degree of this thing, finally to contribute to the degree of this contracted vertex. So, therefore, let us see whether analyze the case. Suppose there is this T x I 2k and there is this T x j 2k. So, is it possible to have two edges going like this? So, if there are, so the tree here may be like this, right, and yeah, if there are two such trees, then the problem is yeah. So, what will happen to this cycle? So, this comes to the root or wherever the common ancestor of this thing, and then come here, and then similarly this will go to the common ancestor of these two vertices and then come this tree. And this root, this path is at most 2k, this path is also at most 2k, this is at most 2k and this is at most 2k, and these are here 1 and 1. Total 8k plus 2, that is still less than 8k plus 3. So, because the girth is greater than 8k plus, this cycle cannot exist. So, this will not happen, this will not happen. That means, from this tree you can only have one edge going to the other tree, any other tree. So, in the contracted graph, to know the degree of this vertex, the contracted vertex, this vertex, we just need to count the number of edges going out of it. If we get a lower bound on the number of edges going out of it, we get a lower bound for the degree of the each vertex, right. How do we find the lower bound for the number of edges going out of it? That is done like this, because for instance, this T x is first T x 0, then T x 1 0, then this is here we got T x 1 1, then we in the next stage we got T x 1 2. So, up to the ith stage, suppose we say when we are considering the k minus 1th stage, we had our tree finally is T x 2k, but consider this tree T x the stage at which the k minus 1 step, how many of the neighbors will be captured. So, any vertex at the kth stage, does it get two choices? That is the question. Suppose this got attached to this tree at this stage, this got attached to this tree at this stage, but is it possible that this could have been attached to another one? So, the point is it cannot be, because the distance from here to this tree is at most k. So, exactly k, that is why it is getting attached to this tree, but then if suppose there is another y to which y tree from starting from y to which it can be attached, then the distance from here to here also will be k, and the total distance from this point to this point will be k plus k equal to 2k, but that is, we know that this distance has to be at greater than 2k. So, that is not possible. So, all the vertices at distance k from this x will be attached to this tree only. That means, at least in the kth, when you are moving from k minus 1 stage to kth stage, we will be capturing at least how many vertices, because here we have all the vertices up to here, all the vertices will be there. This is the number of leaves of starting from here. If we had captured all the neighbors at every stage up to here, that is like that only, because the first level we will get all the neighbors, then at this level all the neighbors of neighbors will come, at this level all because they won't be claimed by another tree, because they are too far away, all other trees are too far away from at this up to this k minus 1 level. So, therefore, this number of vertices can be easily estimated, because that is at a distance of k, that is definitely d into right. So, right d minus 1, because here the first level we have d and the d minus 1 raised to k minus 1, right. So, the first level we have d, in the second level, and then the number of edges how many edges will go out of it. So, that is very clearly the required number. So, this number will come. d into d minus 1 raised to k, because you have to multiply again by d minus 1. So, this will give you the minimum degree, lower bound for the minimum degree of h. We will get a minimum degree of the lower bound for the minimum degree of h. So, we do have a h minor for G with where the minimum degree of h is greater than d into d minus 1 raised to k. This k comes from the girth, because the girth is defined in terms of k, 8k plus 3, right, and d is the minimum degree of G itself. So, that this we have a minor whose minimum degree is exponentially higher, I mean that exponent is coming from the girth than the minimum degree of original graph, right. We somehow concentrated we made the graph dense, and now we can apply Kostochka's result on this thing, because there is a graph with high minimum degree. So, the average degree should be high, then we can just estimate what would be the minor, the clique minor that we will get from this thing. So, that is the next statement. So, this statement is Thomason statements can be obtained from this thing. So, let us look at this thing. We will take this FR. Thomason statement says that if the girth is greater than FR, we can find a KR minor, that even with the minimum degree requirement 3. Initially, let us say the minimum degree is just 3, d equal to 3. In distal statement, we can take d equal to 3. So, then we just define a k such that we will define k equal to k of r, such that 3 into 2 raised to k is greater than or equal to 2 into see, this is that constant from Kostochka's theorem, and then r times root log r. So, this is coming from this statement. Yeah, this statement, this C r root log r. So, the Kostochka wanted the average degree greater than equal to C times r times log root log r, right. The same function we take, and we find out the k, smallest possible value of k, such that 3 times 2 raised to k is greater than equal to C times r log. Because why? Because distals in this previous lemma, in the distals lemma, our d will be put 3 now, because we are thinking about graphs with minimum degree at least 3, and d minus 1 will become 2. So, it is 3 into 2 raised to k. So, we want to find out what is that k, because and then we want to verify whether the girth requirement will be okay, right. So, therefore, we will find out this thing. If this is the case, we know that we do have a KR minor here, right. So, for in H, because we know by Distal's proof we do have an H with minimum degree greater than equal to 3 times 2 raised to k, and then therefore, we do have because this amount is greater than equal to this value is greater than equal to this. By Kostochka's statement, we have a KR minor here. The only question is whether to apply Distal's result, we need one more thing. The girth has to be greater than equal to 8k plus 3. So, here this is in Distal's theorem, this is d equal to 3 we put, this is d minus 1 and this is k, right. But this k also should be connected to girth. Girth should be greater than 8k. We just verify this. So, what is k? We just take a log here. This k equal to, from this thing we get k equal to, so we will go to this thing. So, we have this greater than equal to C times r root log r, right. So, now we can take this to this side and then take log on both sides. We get the k is the smallest value, such that this is greater than log r and plus half of log r, right, because log of root log r is half log r minus, it is a plus log C by 3, right. So, there is a constant here. now we can estimate. So, we will put some seal or seal value for this thing. So, approximately if I take 8k plus 3, we can easily see that this will be greater than or equal to our alright. So, the so our girth, this value will be like here, you know, 8k plus 3 is going to be at most. So, we can substitute this thing 8 log r plus, you know, multiply this 4 log r plus some constant, right. We can fix the constant so that it is less than this. Now, this is indeed the f of r we have selected. So, we may have to place a constant, some c dash in such a way that we are above it, this function is above it. So, if you had selected the f of r, the constant here in such a way that this is bigger than 8k plus 3, as we have seen here, we can make it bigger than 8k plus 3. So, then the distal lemmas can be applied, and then this because our 3 into 2 raised to k is the minimum degree, then Kostochka's lemma says that we have a kr minor, right. That is what we get. So, then so this is one example of showing that we have a dense minor. So, here that is interesting because the girth, you just have to keep the girth high even if you keep the minimum degree at 3, right. Then we do get large minors. We can, whatever minor we want, we can, depending on the, so as a function of the r kr minor we want, that r we have to define the girth. So, here is another statement which is interesting. So, if suppose if we want TKR, then we know that if you want TKR, your degree requirement will be so because each of the branch vertex has to be of degree at least r minus 1, right. So, if you just have the minimum degree requirement the same as that, delta greater than or equal to r minus 1, and then if the girth is a little high, we do not even have it as a function of r, if it is some constant exists such that if the girth is greater than that constant, then we do have a TKR, right. So, this is also an interesting result. And now, the so that these are some known results from the graph minor theory. So, in the graph minor theory, there is an interesting results called a graph minor theorem. So, in this, because we do not have much time now, only around say 20 minutes are left, around 15 minutes we will get now. So, therefore, we will not get into the technical details, we will just quickly introduce that the concept. The thing is, for instance, it is much easy, very easy to understand it from the idea of this what we know about planar graphs. So, planar graphs are some kind of minor closed graphs, because if you take a minor of a planar graph, it is again a planar graph. So, that, but then we know that a planar graph can be characterized by two forbidden minors, namely k5 and k33. We have studied it before. That means, planar graphs cannot have k5, planar graphs cannot have k33. Not only that, if it is a non-planar graph, there will be k5 or k33 as a minor. This is what. So, the planar graph, a graph is planar graph if and only if we do not have a minor from one of these things. So, this is listed like this k5, k33. This is the set of forbidden minors for planar graphs. So, any non-planar graph will get a minor either from either this or this. Also, from this list one minor it will have, a planar graph will not have. So, it so happens that if we are given any minor closed class of graphs, family of graphs, then we can get a list like this, not just a list. When I say list, you can then a list with infinite number of members in it. We can get a finite list, that means a list of graphs with finite members in it, such that our graph class can be characterized this way. So, the graph class which is minor closed will be such that none of these graphs in this list, finite list, forbidden set of minors, will be a minor of a graph in our class. On the other hand, for any graph outside our class, if our graph does not belong to this particular class, this particular minor closed class we are talking about, then one of these graphs will be a minor of that. The same thing like the planar graphs. So, this set is called Kuratowski set, because like imitating the Kuratowski theorem, we can say that there is a Kuratowski set of that minor closed property. So, if the property is minor closed, then see none of the graphs having a minor closed property will have a minor from this list. On the other hand, if we do not have this minor closed property for our graph, then one of these will be a minor of this. So, that is a finite list of the interesting thing is that this list is finite. In principle, if you know this list, so to verify whether the graph has our property, namely this minor closed property, we just have to see whether this is a minor of that, this one is a minor of that, this one is a minor of that. Check for each of the members of this list whether it is a minor of that. If it is a minor of that, and then we will, if it is a minor of that, we will say that yes, we do not have the property. If it is none of them is minor, then we will say that we do have the property. So, this theorem was proved. So, of course, the technical statements are somewhat different, but essentially we can quickly understand it in this way. So, this graph minor theorem was proved in a series of papers by Robertson and Seymour, and then the several ideas were developed to prove these results. So, one of the concepts which was developed would be of particular interest, especially if you are doing algorithm, computer science and so on. So, that is called the tree decompositions. Tree decompositions. I will just give a brief introduction to this concept. So, what is the tree decomposition? The tree decomposition, so given a graph G, we are trying to visualize the graph as a tree in some sense. So, we want to collect several subsets of the vertex set of the graph. So, that is what, let nu be a family of subsets of the graphs, but then the subsets are indexed by the vertices of a separate tree. So, I will draw, suppose this is the graph G. Now, there is this vertex sets here. Now, corresponding to this, we will draw a tree, some tree. There exists a tree. The point is, corresponding to each vertex of this tree, we associate some subset of corresponding to this, we associate some subset of the vertices of G. So, the subsets need not be disjoint. So, if this is 1, we may call V1 is associated to this. This is 2, we may say that V2 is associated to this. Here we may say that V3, this is 3, V3 is associated, and so on. Corresponding to each vertex of the tree, we identify a subset. So, the ith vertex we will say Vi, that is here, a subset from the vertex set of G and associated. But we need to satisfy certain constraints. We need to make sure that these subsets satisfy certain properties. Like one property is, if you take the union of all these subsets, we should get the total vertex set of G. It is not that there exists some vertex of G which does not belong to any of these subsets, that is not allowed, right. This is the first rule. So, each of them should go to at least one, each of them, some of them can go to more than one set, that is okay, but there is we do not allow a vertex not to go in any, right. So, that is why the union should be the total, and then for every edge, suppose u v is an edge of G, and then there should be some v, there should be then there should be some I such that both u and v together are part of V I. See, there can be some V j in which u is part, but v is not. There can be some V k where v is part, but u is not, but we are only asking that there should be one at least vertex set collection V I, so that both u and v take part, right, are members of. So, because we are not allowing we are not requiring that a vertex should go to exactly one vertex set, right, we can go to several. So, everywhere we need not this property, but in at least in one they should come together, that is what the second rule says. The third rule says, it's more interesting rule. So, it says this is our basic tree. Suppose this tree, this is ith vertex, this is jth vertex. So, here we have this set V j corresponding to it, here we have this set V I corresponding to this. Suppose some vertex x of G belong to this V j. So, the x element of V g, so is in this thing. So, this is in this subset. So, suppose the same x belongs to this also. Then we want this x to be present, then we want the x to be present in all the vertices in the, so because we have a path here from this to this. So, we want this vertex to be present, suppose this is k1, this is k2, this is k3 and so on. So, we have corresponding subsets also vk3, so vk2 and vk1, vk2, vk3 and so on. So, each of them should contain x here, x here, x here and so on, right. So, in other words, if you take the vertex set corresponding to this, namely V j, and you take the vertex set corresponding to this, namely V I and take the intersection, common vertices here and here, that intersection should be subset of the vertex set corresponding to this, the vertex set corresponding to this, the vertex set corresponding to this and so on. All the corresponding to each vertex in this unique path here to here we should have. This is the third property that we require. So, for a given a graph G, such a tree and the corresponding subsets satisfying these three rules are called, is together called the tree decomposition of G. So, what is this tree decomposition? This tree decomposition essentially is trying to somehow visualize the graph G in terms of the tree. That means, how close is the graph to the tree. For instance, if the graph itself was a tree, so if this was a tree, so what we do is, so of course, how will you get a tree decomposition for this tree? So, we will define a separate tree. For instance, this will be one vertex set, this will be another 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 vertex set. So, when you put together one vertex corresponding to each of these sets I drew, 2 element sets, we can get a tree structure from that, right. That will be the corresponding tree. Now, we can see that whenever so for all the rules are satisfied here. So, every vertex is part of some subset, right, and for every edge u v, so we know we have a corresponding subset here which contains both of them. Now, if you take any vertex, say this vertex, and this was part of this set, right, this is part of this set and this is part of this set. So, of course, there is they are adjacent here. So, therefore, the third property is trivially satisfied. So, this is a tree decomposition of the underlying tree. See, the green tree is the graph in fact. So, the other tree, namely the tree which I drew here, this tree, sorry, this tree is to be constructed from this figure, sorry, this tree is to be constructed from this figure like this. because here corresponding to each of these subsets I have drawn, you have to put a vertex. So, for this thing I have put a vertex for this. So, that let us say this is A, this is B, this is C. So, I will have to put this is A, this is B, this is C, and then this is D. That means between A is connected to C, T, B, right, okay, C, T, B. Like that we can construct a tree from this thing. This will be the second tree, the tree corresponding to the tree decomposition, right. So, here each subset of the which we assigned. So, for instance, this vertex A is assigned to this subset, it contains 2 vertices of graph. And as we have verified, all these sets indeed satisfy the thing. And now it is, so why is this tree decompositions important for us? So, this is a concept developed as part of the proof of while Robertson and Seymour were doing the proof of graph minor theorem, this concept was developed, and then it turns out to be very interesting for people, algorithmic community also. It so happens that if a graph has bounded tree width, low tree width, then we can get algorithms for very hard problems also using this tree decomposition, because it is a very good representation of the graph. Like trees are then we can define, based on this concept, we can define a concept called the width of the tree. What would be the width of the tree? The width of the tree is, so among all the subsets we are associating to the vertices of the tree, we can take the biggest subset that we have used, that cardinality will be the width of the tree decomposition. Now, of course, our intention will be to minimize the width. So, for a given graph we can have several possible tree decompositions. One very trivial tree decomposition is to take the entire vertex in one set and say that my tree is this, and then this vertex corresponds to V of G itself. This will not help us at all, because we are not unearthing any structure of the graph in this thing. But here the width of the tree decomposition will be the entire vertex, cardinality of the entire vertex set itself. So, but on the other hand, here you can see that each of these sets are of cardinality true. The width is defined to be the maximum cardinality among these things minus 1. Okay, that is the technical reason, because we want the trees to get a width of 1, right. So, here these are all 2. So, 2 minus 1 equal to 1 will be the width of each of these decompositions. We can see that if the width is quite small, that means every subset associated to a vertex in the tree is say 2, 3 or maybe a constant. It will be like the graph, you can see a conceptual tree like structure in the graph, that is why you can do that. So, this structure can be made use of to design algorithms. So, strong the very efficient algorithms. So, this is why probably this was very interesting for the computer scientist. So, on other than the possibility of designing a efficient algorithm based on this tree decomposition, it is also useful in understanding the structure of the graph. Several structural questions also can be connected to the tree decomposition. It so happens that if the tree decomposition is low, many other parameters are also low. If the tree decomposition is so the such connections can be in terms of tree width, we can always associate other parameters to this tree decompositions. So, since we do not have much time, we cannot we cannot spend much more time on the tree decompositions and study more, but I would encourage the interested student to start from the textbook of Diestel and study a little bit about tree decompositions, and then there is several papers available on tree decompositions, tree width, which are quite useful in designing algorithms, and then several in general understanding graphs. So, therefore, the student can study himself. Now, what so this I will formally declare that this course is ending here. So, this is the last class and this is the concluding lecture. Now, if in this entire session, if you have any questions to ask, so you can contact me on this email sunil@csa.iisc.ernet.in. I am from the Computer Science and Automation Department of Indian Institute of Science, Bangalore. So the overall we have covered in this course most of the important or general topics in graph theory. Of course, there are several more other topics, but in general the more popular topics like matchings, colorings, Hamiltonian cycles, and minors. So, not in detail, we have touched most of them, probabilistic method, random graphs. So we have some of the topics we haven't touched is probably extremal graph theory. So, we did not get much time for that, and then regularity lemma, such topics were not covered, but anyway, so they are more advanced maybe. So, we can you can study in a later course about that, or you can, so the Distill's textbook gives some of those things. The main textbooks that I followed in this course is Reinhard Distill's graph theory, and also Bondi and Murthy graph theory book. They have a new edition that I have mentioned in the initial lecture. And then of course, sometimes I have used Douglas West's graph theory textbook, and also Bolabash's text is good for, but I have not taken much material from that for this lecture. So, for this series of lectures, but these are all good books. And then right. So, and about exercises, so there are several exercises for exercise problems that you can try for each of these lectures, from which is available in any of these textbooks, in Distill's book or Douglas West's textbook or in Bondi and Murthy's book. So, there is no need for me to give a separate collection of exercises. It is better to what the student can do is, after going through my lecture, the student can read the appropriate portions from the corresponding textbook. Maybe you will get a more better and more rigorous treatment in those books, so that if you read the things, it will be much better. And then the exercise problems also he can solve from those books. That will completely supplement these courses. So, and if you have any more questions, you can send me email at this email address given here, sunil@csa.iisc.ernet.in. Thank you.